Hello, PLP Geometry. Welcome to Lesson 4 in Unit 6. Unit 6 covering circles. And we are going to talk about these ideas called tangents today. So our Lesson 4 is on lines tangent to a circle. Okay, so let's talk about what a tangent to a circle is. So if I am a tangent to a circle, no relation to tangent with trigonometry, right? Tangent to a circle. I am a line in a plane. A line in the plane of the circle that intersects the circle in exactly 1 point. 1 point. And that point is called the point of tangency. Tangency. Okay, so again, if I have a circle, I'll draw a circle right here. Let's call this circle C. So this tangent line, I'll do my best. I'm going to draw it in green. This tangent line is going to kind of graze the circle like this. Let's see how I do. Perfect. Look at that. Boom. Okay? So let's call this line L. So let's say that it hits the circle at point X. So we would say that L is tangent to circle C at X. And that point X would be called the point of tangency. Okay, so we're going to use this picture to talk about another theorem. So I'm going to do the theorem on the next slide here. Okay, so this next theorem, or this theorem, is called the radius tangent theorem. The radius tangent theorem. So the radius tangent theorem says if L is tangent to circle C at X, and this is the same picture we just had, right? Then line L is perpendicular to segment CX. And again, let's recall that perpendicular means we create right angles, right? Okay, so let's draw this picture one more time. So here's my circle C. Let me draw my tangent line again as best I can. Perfect. Again, that's line L. We're going to say it hits it at X. So again, what this theorem says is that line L is perpendicular to segment CX. So if I draw segment CX, these two are perpendicular, which creates a right angle. And again, CX is a radius. So that's why it's called the radius tangent theorem, because L is the tangent, CX is the radius. Now, I want to show you something, right? That now that we've created a right angle here, say that I connect C to some point down the tangent, call this Y. Now I've created a right triangle. Okay? Now, in this right triangle, what's going to happen here is the red part is the hypotenuse. Notice that from C to, say, this point right here, to C to that point, this is also the radius R. But then there's this other length out here. Okay, so let's call this point right here, let's call that point Z. So from C to Z, there's the radius, but from Z to Y, there's this other length. So this length of CY is actually R, the radius, plus ZY. So be aware of that when we do problems, and we'll talk about that in the next problem, or our example, okay, of this. And again, when you have a right triangle, if you remember unit 4, right, Pythagorean theorem. Pythagorean theorem. Pythagorean theorem. And again, we talked about this with the equation of a circle. But a squared plus b squared equals c squared. We will use this in this lesson and in the next couple lessons, I believe, with circles. Okay, so let's do an example problem of this idea. Okay, so this is example 1. So it says, what is the radius of circle R? What is radius of circle R? Okay, and in this picture here, we have a circle. Okay, this is circle R. We're going to say that ST is tangent, so I'm going to draw ST. So there's S, there's T. So S is the point of tangency. I'm going to have a radius RS. I'm going to have a segment RT. Okay, so in this problem, they're going to tell me that this is 24, this is 18, and they want to know what is the radius. Okay, so this is my setup right here. Okay? All right. So what we have to do is we have to be intelligent, right? So two things. Number one, when a radius hits a tangent, we have a right angle right here. So now we have a right triangle. So Pythagorean theorem comes into play. A squared plus b squared equals c squared. Okay, so now we have to label our three sides. So the hypotenuse is across from the right angle. So this S points to the hypotenuse. So this side is C. This side. Now what is that side? Well, from R to this point right here, and they actually gave it a point U. So from R to U, this is the radius. Same thing with R to S. So this side is the combination of R and 18. So your C value is R plus 18. A and B do not matter. I'll let the radius be A and this side be B. Okay, and now we're going to plug in our formula. So R squared plus 24 squared equals. Now, because C is R plus 18, I'm going to put that in a parenthesis and square. That's important. So now what we have to do here is we have to take care of this guy on the side. This is not as easy as just giving the squared to both the R and the 18. That's wrong, right? So I'm going to do this down here in blue. So R plus 18 squared is really R plus 18 times R plus 18. You have to write that binomial twice, and now we have to either distribute it out or use that box method that you might have learned in Algebra 1. So again, I'll just write what the box method looks like. So if you remember, it's like a tic-tac-toe board. We would put x and 18 here, x and 18 here, and we multiply it out. Oh, I'm sorry, R and 18. R, that's R. Now, I'm going to show the distribution method. So to do distribution, I'm going to take this first R and multiply to the second R and the 18. R times R is R squared. R times 18 is 18R. The R is done. Now I'm going to take this 18 and multiply it to the R and the 18. 18 times R is 18R. 18 times 18 is 324. And now I'm going to simplify this by combining the like terms. We can combine these two 18R's to get R squared plus 36R plus 324. Okay, and this is now what that right side becomes. So this right side is now R squared plus 36R plus 324. We call this a quadratic, and it's like, one more thing from algebra, but just wait and see what happens. Now on the left-hand side, we just have to simplify this. So R squared stays R squared. But we do 24 squared, and 24 squared is 576. And now, typically what I would say is, hey, this is a quadratic. Let's get everything to one side and make one side 0, if you recall from your algebra days. However, if you look at both sides have a single r squared. So if you looked to combine those r squareds by maybe subtracting r squared on both sides, they would just cancel. And now we're left with 576 equals 36r plus 324. And this is a lot better equation because this is just a two-stepper, right? If you're someone who likes to draw their line down the equal sign, I need to get this r by itself. So let's subtract 324 on both sides. This gives us 252 equals 36r, and then we'll divide by 36 on both sides. And we get 7 equals r. So the radius here is going to be 7, and it'd be units, but whatever. And there we go. Okay, I have one more theorem to show you, and then one more problem, and then this video is done. I'm going to do it all in the same video. Okay, so sorry if you like me splitting it up, but good if you don't. Okay, so the next theorem is called the two tangents theorem. Okay, so we have the two tangents theorem. And if you can guess by the name, it's going to involve two tangents. So the two tangents theorem says if two tangents with a common endpoint exterior, if two not two tangents. Sorry, go back here. If two segments. I was like, what am I writing? If two segments. I apologize. So please, if two segments with a common endpoint exterior to a circle are tangent to the circle. Are tangent to the circle. If two segments with a common endpoint exterior to a circle are tangent to the circle, that's a mouthful, then the segments are congruent. Okay, so what in the world does that mean? Well, let me draw a circle. Here's my circle. It's called circle P. Okay? And let's draw two tangent segments, right? So I'll draw one up here. And I'll draw one down here. Okay? So they hit the circle there and there, right? Those are tangents. Again, I could keep it going, beyond, but I don't need to, right? And then these are the radii where they meet, right? So we have right angles there. Let's call this PB. We have right angle there. Call this PA, right? And call it PC. And then let's call this point where the two tangents intersect on the outside. Let's call that point A. So we'll call this point C, and let's call this point A. So our two tangents are AB and segment AC, right? They share a point A. This is that common endpoint exterior. What this means is that segment AB and segment AC will be congruent. Segment AB will be congruent to segment AC. Okay, so let's see if we can use this problem, or use this idea in a problem, and we'll be done. Okay, so example 2 says, what is the perimeter? What is the perimeter of A, B, C, D? So I'm going to do my best here. So we're going to have a circle. This circle is going to be inscribed in a quadrilateral. Looks like this. So we'll have a tangent coming up here. We'll have a tangent coming down here. We'll have a tangent coming here. And then we'll finish it off with our tangent here, and I might have to erase some things. I apologize. Boom. There we go. Okay? Let me erase this little piece here. All right. So what we have here is we have two things. We have either a circle inscribed in a quadrilateral or a quadrilateral circumscribing a circle. Okay? And in this problem, they're going to give you the following things, right? They're going to call this point A. So this is A, B, C, D. And in this problem, they gave us this length. They gave us that this was 8. They gave us that this was 5. They're telling me that this is 3. And that this right here is 4. So there's the lengths they gave us. Okay, and they want to know what the perimeter of this is. So you have to notice, and I'll do these in blue, that these are points of tangency. There, 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 and there. Again, if this was the center of the circle, if I draw dotted lines out, these would all create right angles. Right? Those are the points of tangency. We have the two tangents theorem happening once, twice, 3, 4 times. If you look at where A is, A to this point right here is a length of 8. This segment will be congruent to A to this tangent point here. So this segment will also be 8. B, this segment from B to this tangent right here is 5. So this segment from point B to this point of tangent will also be 5. We look at C. This segment right here is 3. So this segment right here is 3. They're congruent. So let me put the markings. So double congruent. We'll put triple congruent. And then here at D, this one is 4. Quadruple congruent to this one, which is also 4. And now we can see that our perimeter is made up of 2 8s, 2 5s, 2 3s, and 2 4s. So to find the perimeter, I'm going to do 2 8s plus 2 5s plus 2 3s plus 2 4s. You can do this however you want to. You can add them all up. I don't care at all, right? And when you simplify this, this will get you 40, and that's units because it's perimeter. So this is how we use the two tangents theorem to find the perimeter of a circumscribed polygon. All right, thanks for watching. Hopefully it went well, and we'll see you in class.